Analytics Conference. My name is Corey Brumbergs. I'm an MBA student at MIT Sloan. And it's my pleasure to introduce this workshop, Winning in Sports with Data and Machine Learning, and Kostas Pelokrinis.
Thank you for the introduction. And thank you for coming. I know it's towards the end of the conference, so thanks for being here. So what I'll be talking about today is a little bit of introduction in some machine learning techniques and how you can use them to analyze sports data. So we're going to see a little bit of coding. I have some examples, and you can either run them now with me, or you can run them later. I have links for where you can find the code and the data. We'll basically talk a little bit about the theory behind the methods and what they can do for you. So first of all, as a very quick definition of what is machine learning for those that are not familiar with it. So basically is a set of methods that help machines improve for a specific task, their performance for a specific task as they gain more experience. And experience in our case obviously is as they get more data. The improvement is always measured based on a specific performance measure, and we'll see there are different performance measures that you can use. In general, you can classify the different types of machine learning methods and models that you have in four categories. Supervised learning, which basically means that you have a set of observations and a set of labels, in the sense that you know what eventually happened for what you want to measure, and you try to replicate, to identify relationships there. Then you have unsupervised learning, where you just have a bunch of data. You don't know what you are looking for, what value it has, let's say, and what you are looking is for natural patterns in the data without having pre-labeled data. Then there is semi-supervised learning, where basically you have some data that are labeled, but the majority of the data are not labeled, so how you can combine both of that. And then there's reinforcement learning, where basically there's some sort of a loop. You take some action, you see the output, and you try to improve over that. Now, machine learning in general have been used obviously in many different applications, natural language processing, computer vision, with a lot of success, obviously bioinformatics, medical data lately, and so on. And lately it has actually started being applied a lot in sports data, and many of these pioneer works actually we have seen them in this conference. So what we are going to cover today is four specific topics. So the first two, we will see them in more detail, and then the last two a little more brief. So we'll start with the very basic statistical learning method that pretty much everyone learns in an introductory course in statistical learning or machine learning, which is regression. So this is the most basic learning technique that you can have. And then we are going to see some other methods that aim at finding hidden patterns in the data. And we'll talk a little bit about Mattox Factorization and how it can be used to analyze spatiotemporal data, which is a fairly important type of data that we start gaining access to. And then we're going to see some other examples that basically use what we call network embedding and neural networks, which are basically examples of this new trend, if you want, deep learning or better representation learning. So the last two, we are going to basically see just the basic ideas and their applications. And if you need more information, obviously, you can ask me offline. So let's start with regression. Our example for regression will be how you can, for example, rate teams with a regression method in order to discuss what regression is. So regression basically is a statistical technique that aims at identifying relationships between multiple variables. Right? So typically you have one variable that you are interested in its value, a dependent variable that you don't know that you want to predict, for example, and you have a set of independent variables that you believe that they correlate, they impact the value of this dependent variable. Regression is a supervised learning method, so if you go back to the 4 categories you said, it belongs to the supervised learning category, and basically what it tries to do is it tries to identify this relationship using past data. So you have a bunch of data points where you have measurements for the independent variable, and you also know what was the value of your dependent variable. So what you are trying to find is to identify the relationship between all these different variables. Now, in order to run regression, you need to make an assumption, right? One of the assumptions that you have to make is what type of relationship exists between the variables, right? And the simplest assumption, the one that you first try out, is a linear relationship between the independent variables and the dependent variable. So, for example, here in this equation, y is the dependent variable that you have. This can be, for example, the rating of the team that we are going to look for. And then you have a bunch of independent variables, x1, x2, and so on, which can be box score statistics, for example, of the team. And you make the assumption that these are related linearly with the dependent variable. Right? Obviously, you can have a different hypothesis saying that it depends on the square of the independent variables or on the power 3 and so on, right? But this is the very basic, the first hypothesis that most of people try out. So the problem when you make this hypothesis, now the learning problem that we talked about in the beginning is basically how you learn these coefficients, right? How you learn this A0, A1, A2, the ones that basically tell you what is the relationship, the exact relationship between the variables. So this is the task T that we discussed in the beginning in the definition of what is machine learning, right? Your task is to learn these coefficients. Now, typically, in order to learn these coefficients, one brute force way would be to try many of them and then see which ones, which combinations give you a good approximation of the actual values, which pretty much is what you do, but in a more principled way. So in order to do that, you need to define what we say cost function, right? Which basically is your performance metric that we talked also on the definition, right? So we said we have a performance measure P that will tell us whether basically what you learned is good. So for example, in the case of regression, what you are interested is seeing how well this linear relationship is at predicting your dependent variable, right? So for example, you have a bunch of measurements and you know this yi, right, which is basically the value for your dependent variable that you measured. And then what you have hypothesized is that this value should be equal to A0 plus A1 x1 plus all the way AN xn, right? So the difference between these two, if this difference is small, your prediction was well. If the difference was large, your model was not good, right? So you can have different cost functions. For example, you can have the square of this difference, or you can have the absolute value of this difference. So in general, the performance metric is something that you decide, and obviously different performance metrics will give you slightly different results. But this is the performance metric you decide from the beginning on what to do, right? So once you have decided this, let's see how you could use this framework to solve a sports-related problem, right? Which is, for example, identify team ratings from past results. So, for example, the team rating, what will give you, it will be expressed in points, and it will tell you basically how many points better than an average team your team is, right? So if you have a team rating that is positive, it means that your team is better than an average team, whereas if the rating is negative, it means that your team is worse than an average team. Now, if you have these values, what you can then do is that you can say if team A plays with team B, the expected point differential in their game will be the rating of team A minus the rating of team B, if A plays at home, plus some value for the home edge, right? It's fairly widely acceptable that in all of sports there is some home edge, which can be expressed in number of points. How many extra points do you get because of playing in home? So in our case, in order to model this as a regression problem, your dependent variable, your observation, first of all, your experience is past results, right? So you have a bunch of games that you have observed, and you have seen who has won whom and by how many points, right? So your dependent variable in this case will be the score differential between the home team and the away team and the visiting team. Now, your independent variables could be the ratings that you are looking for, right? The ratings of the teams that you are looking for. So now, if we consider, let's say, the NBA with 30 teams, you can consider that you have 30 variables that are dummy variables, so they are categorical. So if you have a game where, let's say, Chicago Bulls are playing at home, the corresponding variable will be 1. And if the visiting team is Minnesota, the corresponding variable will be -1, and all of the other variables will be 0. Right? So this is the data set that you have. Your independent variables are the teams, and indicators whether the team is playing at home, is playing away, or it's not playing at all in the specific game. And your dependent variable is the score differential between the teams. Now, if you solve and you learn the coefficients of this regression, then you can have a prediction, as we said, for what would be the outcome of a game between these two teams by having the home edge, that as we will see, we can learn through the regression as well, the home team rating minus the away team rating. So in order to do that, what we are going to do is basically, we are going to rely on the cost function that we talked earlier, right? And essentially, we are going to basically take all of the games that we have in our data set. So let's say that we have 800 games, the first 800 games of the NBA season. We're going to find for every game what is the score differential margin, right? So how many points in matchup I the home team win by. Oops, sorry. And then our prediction for this game would have been the home edge that we don't know, the home team rating minus the away team ratings, right? So all of these are variables that we don't know, right? Now we also have a constraint here that we want an average team to have a rating of 0 in order to be able to understand better these values. So we have a constraint that all the sum of these ratings should be 0. So we'll see how we can solve this in Python. As I said, you can find the data and the code here. These are actually data from the current season. Actually, it was up until the 7th of February. So it includes all the scores for the first 800 games of the season. So when you download the data, you will see that the data set with the results is basically a CSV file which has the home team, away team, how many points the home team scored, and how many points the away team scored. And what you can do is you can use pandas, which is a library in Python, to basically read this as a data frame, which stores very nicely the data. And then what I'm doing there is that I'm just finding what are the team names, just as a sanity check, right? So you will see that the data set looks something like that, where you have the home team, how many points the home team scored, the away team, how many points the away team scored. And this is the list of teams. Actually, it's fairly small. You cannot see it. But trust me, it's the 30 teams, the 30 NBA teams. Now, once you read this data, what you need to do is you need to index this data, right? Somehow you need to basically assign a number to every team, because this is easier to manipulate when you do the optimization rather than using strings. So this snippet of the code, basically what it does is that it goes, and what it creates some index, right? So instead, for example, for the first line saying Boston Celtics against Cleveland Cavaliers, we say team 25 against team 6, right? So we just enumerate the teams from 1 to 30. Now this is the main part of the code, where basically you have to define the objective that you are trying to minimize, right? you have to define the optimization problem that will make you learn these coefficients. And here, it's, basically what we are doing is that we are defining this error, this cost function, where basically you're taking every row, right? So we are taking every row of this data set. We are calculating the actual score margin, right? So in the first game, it will be, actually the home team was Cleveland, 102 minus 99, it will be 3. So this is the first part, df of gh, df of ga, right? And then this is your dependent variable. The rest of it is the independent variable, which basically is the home edge, which is a variable that you are looking to find what is its value, plus the rating of the home team, which is the rating of the Cleveland in this case, in the first row, minus the rating of Boston in this case. And then we have also squared this because we said the cost function, you can either take the absolute value or the square or another non-negative metric. And in this case, we take the square. We also define the constraint that all these ratings, the sum of this rating needs to be 0, right? So the first part defines the objective function, and the second part defines the constraint for the optimization problem. Now, before you solve the problem, you need to create the vector that will keep the values of your solution, right, the coefficients. And in this case, what we are doing is we're just creating a vector with dimensionality of 31. And why 31? Because you have 30 teams, plus you are looking for the home edge, right? So this is another variable in your optimization problem. So that's for the home edge. And then Python and Scikit has a library that solves this optimization problem for you, where basically the first input is the objective function that we defined. The second input is the vector that you will store these values. And if you have constraints, which in our case we have, you can also add these constraints there. Now, there are many different algorithms through which you can solve this optimization problem. We won't get into the details of that, but typically you can use the least square optimization to find this solution. Now, in the options you have here, we have set an option of maximum iteration. So the solution of the optimization problem, what it does is that it iteratively tries to find the optimal solution, and obviously it needs at some point to stop if it keeps finding smaller and smaller solutions. And here we just have a limit on how many times you do that. So if you run this code, what you will do is that you will get a solution like that, where basically it will give you the coefficients of what you are looking for. So the home edge, you can imagine it being the constant term of the regression, right? It's the constant term that you get because you are playing at home. And we see that in this case, for this year, for this season, this home edge is about 2.2 points, right? Which actually this is an interesting thing because, for example, if you consider what Vegas is doing when it's trying to create projections and point spreads, they're considering a fixed home edge of 3 points, right? But this doesn't necessarily mean that it's exactly 3 points, right? So you can see how this might change from year to year by solving a similar optimization problem. So for this year, at least for the first 800 games, the home edge was about 2.2 points. And then you get a bunch of ratings for all the teams, right? So for example, until the 7th of February, San Antonio had a rating of 2.3 points, which basically means that San Antonio was 2.3 points better than an average team, right? Whereas back then, Cleveland had a rating of minus 94, which basically meant that until then, Cleveland was 0.94 points worse than an average team. So the way you can use these ratings is if let's say San Antonio was playing at Cleveland, now you could use this rating to get an expectation what would be the expected point differential between the two teams, right? So for example, in this case, if Cleveland is playing at home, it will get an extra 2.2 points because it's the home edge, plus their own rating, in which in this case it's negative, minus the rating of the visiting team, in this case is 2.36, right? So all of this gives you a negative value, which means that the favorite in this game would have been San Antonio with 1.1 points. So this is one way to use regression to find the ratings, but you can go a little bit further if you want to translate this to win probability, right? Many people do not, obviously when you have an expected value, doesn't necessarily mean that this is what you will realize, so you are more interested in probabilistic interpretation. So there is this interesting work by Stern. He did it for football, but there are follow-up works that have done it for NBA, college basketball, college football, and other sport. And what he found is that if you have this type of regression ratings, typically the actual win margin follows a normal distribution with an average of the point spread that you find and a standard deviation, which for basketball is around 12 points. So he found for football it was 15, other people did it for basketball, for NBA, and it was around 12 points. So you can translate this expected point margin to a win probability using this normal distribution, and in this case it would have been about 52-53% for San Antonio Spurs, right? So it was fairly equal. It would have been a fairly equal match. Now, what we did with this type of regression is that we found one single number to describe every team, right? So we had one coefficient for every team. But what you can do is that you can do a little more detailed analysis, and you can actually have two coefficients for every team. So you can rate the offense and the defense of the team. So if you do the offense rating, you basically what the offensive rating will tell you is how many points better than average the offense is, whereas the defensive rating it will tell you how many points less than an average team your team allows, right? So a defensive rating would be good if it is negative, an offensive rating it will be good if it is positive. And the way to do that is basically by just tweaking a little bit your optimization function, where basically instead of having just a single rating for the points that you predict a team will score, now you predict that basically the home team will score as many points as its offensive rating plus the defensive rating of the opponent. So basically now instead of just having one variable, you have two variables. You can solve exactly the same optimization problem and you will get two values. Now one of the problems that you have when you want to find this kind of ratings is at the beginning of the season you have very few data, right? The first week or even before the season, how do you get these ratings, right? So there are some ways to do it. We're not going to get into that. Again, I have some code online if you want to use, but the idea is you can use some information from the betting market together with regression modeling in order to get these pre-season ratings, right? Another approach would be, for example, to calculate the ratings from the previous season and translate them with some weighted average to ratings for this season. Now, one of the main problems one of the problems that people that first introduced in machine learning have is what we call overfitting. And this can even happen when you have a very simple model like linear regression. So what overfitting means is basically that instead of learning patterns in the data, your model just imitates the data, right? So just mimics your data. So the relationship that you learn is fitted to the data set that you have. And if you try to apply this to a different data set, it's not going to work well. So many times in order to avoid that, you use what we call regularization, where basically means that you tweak a little bit the objective function that you have, and instead of just solving what I showed you earlier, you have this last term there, where basically what you are doing is that you are adding some sort of the sum of all the coefficients that you find. So now what this will do is that it will force the coefficients to take smaller values. So typically overfitting, the way that it's being realized in a model is that it has very large coefficients, right? Because it tries to create a curve which basically tries to fit each data point that you have. Now by having this term at optimization, if you try to minimize it, these coefficients will try to be shrunk, right? And regularization is going to help you learn rather than just imitate, memorize basically your data set. Okay, so that was the way that you can do regression, right? And you can do it directly with solving the optimization problem. And the reason that I showed you that is because I feel you have way more flexibility on how you learn these coefficients, right? Obviously, there are libraries that you just give the data, it finds the coefficients, and you're good to go. But typically, these come with their own cost function that you cannot change, whereas if you write this from scratch, you have more flexibility, right? So I think that trying to solve the optimization problem rather than just fit the data to a library is a much better way to do that. Now the second topic that we are going to discuss is a topic that is not usually discussed in an introductory class in machine learning, but I believe it's very important in the context of sports data. And this is matrix factorization. And basically the idea is that you can use these kind of techniques in order to identify some sort of hidden patterns in the data, and patterns that you can actually interpret rather than just an abstract notion. So the way that the reason that this type of methods were introduced was basically to reduce the dimensionality of the data. You can imagine that you have some entity that you describe through a vector with 100 dimensions, 100 dimensionality, and you want to find a more compact representation of this entity, right? So this more compact representation, it's called in the terminology of machine learning a latent space for this data. So for example, in what we're going to see here in this tutorial, you can imagine that you have a player or a team shot chart, right? And you describe the player or the team based on the locations from where these players took their shots, right? Now this is too cumbersome in the sense that, for example, if you put a very fine grid on the court, you can have a very high dimensionality, right? So if the court is 94 by 50, if you have basically 1 by 1 feet, then you have 94 times 50 dimensionality, right? Which is very large. So the question is basically how you can create a more compact representation that actually can give you also some insights on the patterns that these players have. So for example, in this case, we can represent the data through a matrix, which basically every row of the matrix represents a player or a team, depending on what you are interested in. And the columns represent different locations, right? For example, if you use the grid, it will represent different grids on the court. And the actual value of this element ij will be the number of shots that this player took from this location. So for the columns, right, so for the location, there are two options. Option one is to use the court zones, the official court zones of a court, which will give you much smaller dimensionality, like 13 columns. Or you can use grid cells, as I said, where if you use very fine grids like 1 by 1, you will have more than 2,000 columns. Obviously, you can tune the grid size to get less or more, but in general, there is some flexibility on how you pick the location granularity. Now, for this, in order to have better visualization, so in this tutorial, I will show you how you can do it when you use 13 columns, right? So the actual zone areas of the court. And let's see how you can do that. Oops. Okay. So first, let's see. So basically, the idea is that we will have a matrix Number of rows will be the number of players that we have in the data set. Number of columns in this case will be 13, which is one for different offensive zones on the court. And what we're going to use is that we are going to use matrix factorization on this matrix in order to find the patterns we're interested in. So matrix factorization, what it does is that it takes a matrix and it just expresses this matrix as a product of two other matrices. And these two other matrices will have information about the patterns that you are looking for. There are several methods for doing matrix factorization, way more than I know. And the one we're going to see today is non-negative matrix factorization, which is good for cases where you have count data, because count data are non-negative, so non-negative matrix factorization is a good approach and gives you interpretable patterns. If you have negative coefficients, it might be hard to interpret the results in this case. So this is exactly what matrix factorization is doing. So you have the original matrix, right? Let's say n rows, m columns, matrix X. And what non-negative matrix factorization is trying to do is trying to find two matrices, let's say W and H, which, if you take their product, is as close as to the original matrix, right? So you want to approximate essentially matrix X with two matrices whose product will give you matrix X. So what you're trying to do, basically, is to solve this optimization problem. So you're trying to minimize the distance between the original matrix and the product of these two matrices, right? So you're trying to find W and H that minimizes this expression. And you have a constraint that all the elements of these matrices need to be non-negative. You cannot have negative things. Now, once you find it, and we'll see how you can find them in Python, matrix H will have what we call the shooting patterns. We will see that the rows of matrix H can give you a nice interpretation of what are the patterns of the players that take the shots, whereas the matrix W will show you which players follow which patterns, right? So it will be a new representation of the players in this new set of patterns. So to understand this better, let's visualize it. So we have the original matrix X, this green matrix with n rows, n players, m columns, 13 zones. And what we are looking for is we're looking to find these matrices W and H. So every row of W, again, will represent a player. And the columns of this matrix will give you some new coefficients for this player, some new representation of this player. Now, matrix H, every row will correspond to a shooting pattern. So, for example, let's say this row might represent patterns, this pattern which basically tells you that this pattern represents shots being taken from the right baseline, a little bit of the mid-range, and some of the left baseline. Right? So this will be one row, and every row will give you a different pattern. Now, the rows of matrix W will tell you how much every player is represented on each of these patterns. So we'll see one example. So, for example, by using some shot data from the NBA and by trying to identify 10 patterns and doing this approach, we found these patterns, right? So the matrix H had specific rows, and these were the rows if you visualize them. So, for example, the first pattern shows a shooting, let's say, pattern from the paint. Then you have patterns like the one at the bottom left, where basically it's the corner threes. Then you have the middle pattern at the bottom, which is mid-range shots, and so on, right? So these are essentially, each one of these patterns represents a row in the matrix H. And now this matrix is basically the matrix W, right? So every player is a row, and you get some coefficients that tells you these coefficients how much every player is represented in these patterns. So, for example, in this case, Steph Curry, you see that the majority, the main, the higher coefficient is for pattern 2, which is 3 points from the right elbow. Trevor Ariza, the second column is the same. LeBron James is mainly in the paint. Then you have Chris Paul, for example, the last column where you see he's a mid-range shooter from baseline. LaMarcus Aldridge, you see the majority is mid-range shots. So these are passing a little bit the eye test, right? So every player in this way, you can represent him as a combination of these 10 patterns. And the value of the coefficient tells you how much they are represented in each one of these patterns. So let's try and do that on our own now. So how I can compute these matrices in Python? Now to switch up a little bit things, I have provided you with some data from a European competition. Everyone is doing things with NBA data, so let's switch it up a little bit. So this is an international competition, the FIBA international competition, 32 teams. So these are data from this season, the regular season, about 25,000 shots and about 500 players. So again, data and code is online. And let's see what you do. So actually, this is an even simpler case than running the regression. Basically, Skylearn has a function that does everything for you, so you don't need to do a lot of stuff. So you input the data again in a data frame using pandas, and basically what the main part is this NMF function, which does the factorization for you, right? So solves this optimization problem for you. Now you have some parameters that you have to set there. So for example, the first parameter is how many components you are looking for. So in this case, I have put 7, and I will tell you why I put 7 in a while. How many times you iterate in order to solve the optimization problem. Because again, remember, matrix factorization is solving an optimization problem, similar to regression, so you need to have some sort of iteration there. How you initialize this optimization. For example, in this case, we did it randomly. And then you see, using this NMF function, you find matrix W and matrix H. So this is how it will look like. So you can find matrix W will basically be a matrix where the number of rows is equal to the number of players, and the number of columns is equal to the number of patterns that you are looking for, whereas matrix H will be number of rows is equal to the number of patterns you are looking for, and number of columns will be the original dimensionality. So here is some similar examples as from the NBA data, but this is what you will get if you run the code I'm giving you. So for example, the first row, this player is actually a mid-range shooter mainly. Then the second player, you see the majority, the highest coefficient is for points close to the paint, and so on. So you can get some idea for players that you don't know, right? So you can get some idea whether they are efficient, for example, where they are taking their shots, and so on. Now, one of the questions is why 7 components, right? So this seemed to be an arbitrary decision, right? Now remember that non-negative matrix factorization in general is an optimization problem. You are trying to approximate a matrix, right? So one thing that you can do is that you can calculate the reconstruction error, right? So you have the original matrix, you have the factor matrix that you found. What is the distance between these two matrices, right? What is the Frobenius norm of these two matrices? So for example, we can do the following. We can find different factors for different number of components, and then find how the error looks, right? So if we do that, which actually this part of the code does that, we see basically that obviously the more components you are using, the better the approximation, right? But this comes with a cost, right? The fact that you have a low reconstruction error doesn't necessarily mean that you have learned something. It might just mean, as before, that you have overfit the data, right? So for example, in this case, it's clear that if you use dimensionality more than 13, which is the original dimensionality, you are going to overfit the data because you are able to exactly reconstruct everything that you had in the data. So there is a trade-off that you have to pick there, right? So you want to have low error, but on the other hand, you don't want to overfit the data. So if you do that, you see that 7 might seem like a value that you haven't overfit the data, but also gives you a good reconstruction error. Now, there are obviously better ways to avoid overfitting, and again, this way is regularization. So regularization, you can not only use it in linear regression, but you can use it in any optimization problem. Right? So for example, in this case where we are going to solve this optimization problem between the matrices, you can add a regularization term where basically will be a term for all the values of this factor matrix that you are looking for. Right? So this RWH will be a regularization term which can be the sum of the squares of all the elements of this factor matrix that you are looking for. Now, other ways to do this factorization is instead of focusing on this Frobenius norm, right, the specific distance between two matrices, you can use other distances between matrices, right? For example, you can use the KL divergence of the two matrices. And actually, it has been shown that KL divergence works better when you have matrices that you have count data in them. Now, obviously, you can do even better than the simple approach that I showed you to introduce. So, for example, one of the problems is that if you use fine-grained grid over the court, right, as I initially said, one of the problems is that you will have a lot of sparsity, right? So you will have data, you might have very few data points in one grid, in the neighboring grid, again, few data points, but there are not really big differences in the location, right? So what you can do in this case in order to avoid sparsity is that you can smooth this curve, this grid, using things like a stochastic Gaussian process, for example. So this work that was presented at ICML from Franks, Miller, Born, and Colesbury in 2014 did exactly the same thing as what I showed you, but it had a smoothing pattern over the grid in order to get more interpretable results, right? So you can see that in this case, you get a little bit better fine granularity for the patterns, right? Instead of having just the zones, you actually have more details on the court. Now, you can also go to higher dimensionality, right? You can imagine that shot selection doesn't only is not only affected by the location of the player, but it can be affected by the game clock, by the shot clock, by the current point differential, by many other contextual factors, right? And matrix has only 2 dimensions, right? So you cannot incorporate all of this. So what you can do, for example, is that you can use the generalization of matrices, which are tensors, and you can use similar techniques to identify similar patterns. So for example, in this case, you have, again, shot charts, and you have a 3-dimensional matrix, a tensor, where basically every element of the tensor, the I, J, K element will give you the number of shots that player I took from location J during time K, right, when the game clock was within specific time period. And then, if you do similar factorizations, but now for tensors, you can identify, again, patterns in the sense that you can identify a set of players that take shots from similar locations during the same times in the game. Right. So obviously, this I have a reference there if you are interested in, but this is the next step from matrix factorization. Okay, and the last part, which, as I said, I don't have code for that, but I want you to just get an idea what is the difference between whatever other things are happening in machine learning and what is happening now, is this deep learning, right? I actually saw that in this conference, maybe half of the papers were using some kind of deep learning methods. And the difference between deep learning and traditional machine learning is that in deep learning, you are not trying to create a model in the traditional sense that I showed you before, that you have a dependent variable you have some predictors and you're trying to find the right relationship between them, but deep learning is trying to actually find the best representation of the data, right? So it tries to identify basically your features, right? So you give the raw data and it tries some way to identify what is the best representation of this data that can do the task for you. So in traditional machine learning, we are using a combination of obviously modeling, feature engineering, and domain-specific knowledge, right? So for example, you know that offensive rebounding rate impacts winning, or effective field goal percentage impacts winning, right? So this is some domain knowledge that you use in order to build your features. And then if you have a large set of features, you can do things like cross-validation to find which one of these are predictive. Now in deep learning, you don't have to do all of these things. Deep learning, supposedly, you can imagine it as some sort of a brute force technique which finds the best representation on its own. It has been used in several fields before sports, with the one that had the most success being computer vision. So it was able to build classifiers for vision tasks, and recently, obviously, has been used in sports. So what we are going to see two examples of deep learning methods that can be used in sports with some good results. Now, what I'm going to focus a little bit in the beginning is a different deep learning or better representation learning than what you might imagine like neural networks, right? We will focus a little bit on networks, which basically represent relationships between objects. And the reason I like to talk about networks can actually be realized through this example. So here I'm showing you two pictures, right? I'm showing you a picture of a pencil and a picture of a diamond. Obviously, we all know that they have different value, right? They have different properties. But do they have anything in common? They're made of carbon, right? Apart from the obvious differences, what else do you think is different? The what? The process they went under, which had as a result different connections between the carbons of atoms, right? So they are made out of the same basic unit, but the way these units interact and are connected with each other are completely different, right? And these different relationships, they give different properties in the whole system, right? So depending on how they interact, what is the network connections that they have, you can have the whole system having a value more than the sum of its part, or having a value that is less than the sum of its part. Right? So when you have team sports, you're interested about the system, right? So when you have team sports, when you have single player evaluation metrics, these might not necessarily give you an idea on how these individuals will perform when they are put together on the field, right? Whereas networks might give you some better idea about that. So one problem, though, with networks and why they have not been used a lot in sports is the fact that the way that networks are being represented, it is hard to pass them through traditional machine learning techniques, right? You cannot take a network and put it through a regression, for example, right? So this is where deep learning comes into play, and what you can do, there are methods now where you have a network, and you have the nodes of the network, the entities that you are interested in, and you can first process this network and get a representation, a vector representation, for each one of these nodes. Obviously, there is some objective there on how you get this representation, but the idea is that you can use these deep learning techniques, which basically take a network as an input, and what it gives you as an output is a vector representation for every node. Now, if you have a vector representation for every node, you can use models, machine learning models, to basically do things like prediction or understand what impacts specific performance metrics and so on. So network embeddings, there are many ways to find them. You can find them with Mattox Factorization, random walks, which is what is the main approach today, and neural networks, which is something that people have started looking lately. But the idea is that this is a deep learning method, because what you are doing is that you are learning a representation of an entity, right? And deep learning is about learning a representation. So, this doesn't look right, but let's fill it up. So the way we use this network embedding, you can use this network embedding is, for example, to do probabilistic lineup evaluation. Right? So what you can do is that you can take lineups that have played with each other, and you can build a network. For example, here we have 3 lineups from the Celtics, Lakers, and Spurs. And let's say if the lineup from the Celtics have played with this specific lineup from the Spurs, there will be an edge between them. And the direction will basically show you which lineup outperform which lineup. Right? So you can build this network, and then what you can do is that you can basically use this network embedding to represent every lineup through a vector. And now, since you have vector, what you can do is that you can put this abstract representation through a regression model and build a probabilistic model of which lineup is going to outperform which lineup. Right? So one of the most popular ways to find this representation is this node to vec, which actually, if you saw the pitcher to vec, batter to vec paper is very similar to work to vec. Actually, it was derived from that approach. Node to vec is doing exactly this thing. So it gets as input a network, and it gives you as output a vector representation for each one of the nodes in the network. Now, obviously, there needs to be some way to find this representation. So you solve an optimization problem, and the optimization that you are trying to solve basically there is that you are trying to be able, using these features, to recreate the neighborhood of every node. Right? So you have some structure in the network, and you want to find a representation that through this model, I won't get into the details, but basically the probability of 2 nodes connecting being high whenever they have similar representation in this space. Actually, the nice thing, I won't show you code, but the code for this approach is online, so you can find it on this GitHub page. So you can use it, you can take a network, run this code, and it will give you a representation of every node. So if you do that, as I said, you get a representation for every node, for every lineup in our case. You can pass it through a regression model. I see the time is running down, but it's a very simple regression model where basically lineup I plays with lineup J. You have these vectors, you take their difference, and this is your independent variables. So if you do that, you can basically do some probabilistic predictions, and then you can basically evaluate these predictions. There are 2 ways to evaluate these predictions. The one is the accuracy, which is not always the best way to evaluate this kind of predictions, even though it works good. Overall, when you are caring about the probability, maybe the accuracy is not the best way to go with it. So, for example, in this case, we have evaluated the performance of an embedding-based lineup evaluation with the typical ways that you evaluate lineups. For example, plus minus, or O plus minus, or adjusted plus minus of the lineups, not individual players. We see that obviously the rho plus minus doesn't do a very good job in terms of accuracy. Adjusted plus minus improves quite a bit, but the what I call the linet, which is the network embedding, performs even better in terms of accuracy. Now, the most interesting thing, though, in terms of probabilistic calibration, it's how good these probabilities are, the probability of outperforming another lineup. And this is where the Breer score gets into the game, where basically Breer score gives you how good the probabilities that you output it are. And the smaller the Breer score, the better the model, right? And in this case, we see that with embedding, you can have a better calibration. Now, this is also the calibration plot in terms of predicted probabilities versus actual probabilities. So what this plot does is that for every matchup, for example, that we predicted, that the home lineup will outperform the visiting lineup, let's say, with 60% probability. How many of these matchups actually the home lineup outperform the visiting, right? And ideally, if this probability is correct, we want to have about 60% of the cases being correct, right? Because this is the probability we gave. So you want this curve to be as close to the y equals x curve as possible. And we see that it does fairly well, very good linear fit. Now, the intercept is not exactly 0, obviously, but it's close to 0. And the Slope, again, it's not exactly 1, but it's close to 1. And I'm pretty sure if you add more things in the embedding, like regularization and other kind of stuff that we discussed, you can do even better. So that's one way of learning a representation from networks to an actual vector representation. But other ways, obviously, are neural networks. So there are many papers last year and this year that have been presented about ghosting. So, for example, this is from Grantland a few years back, where basically what the Toronto Raptors were doing manually was basically identifying for every possession which should have been the best location of the defender. And this way they try to evaluate how good defense a player was playing. But now you can do that with data. Actually, in this conference, there was a paper, Ghostbusters, I think, Ghostbuster basically, but a little bit a different name for copyright reasons, that did this for basketball. And last year, actually, there was a very similar paper here where basically they were using a neural network to learn this, to learn a representation of the defense that was able to identify these ghosts, these locations that the players should have been at. So neural networks, what I want you to, deep learning in general, what I want you to remember is that it's learning a representation. It's not necessarily modeling in the traditional sense that we have seen in machine learning, but it's learning a representation of the input data and finds for you the best set of features, the best combination of features that will help you with your task. So that was all. So if you have any questions, obviously you can send me an email. And many of the things that I showed, and obviously other things that I didn't have to show, a shameless promotion of my class, you can find it on this website. So there are way more things if you're interested in that.